Good morning, all. Today's topic are single phase half wave control rectifier with a general load. So, in this lecture, we are going to discuss about the single phase half wave control rectifier. In previous lectures, we have already discussed about the single phase half wave control rectifier and what is the difference between your control rectifier and uncontrolled rectifier, and what is diode and how diode is used to control how diode is used in rectifier, and what are the difference between controlled and uncontrolled rectifier, and uh, so many things we have already discussed. So and the content of this lecture is half wave control converter, full wave control converter, and analysis of single phase half wave converter with RLE load. In previous lectures, after this lecture, I'm expecting from student that student would be able to understand that what is your control rectifier and how it works with RLE load and what are the waveforms and how can we can analysis all the waveforms of converter. So, student will be able to understand the concept of controlled converter. Student will be able to understand waveform with R, RL, and RLE load. Student will be able to analyze the waveforms. So, this is our we controlled converter. So we have already analysis this these waveforms with RL load. So the average output voltage we have already derived in previous lecture. That was the equation. VDC is equal to Vm upon 2 pi 1 plus cos alpha, which is the same as that of purely resistive load. So the following points are to be noted. For low values of inductance, the load current tends to become discontinuous. So during the period alpha to pi, the load current is carried by the SCR. During the period pi to beta, load current is carried by the freewheeling diode. The value of beta depends on the value of R and L and the forward resistance of the freewheeling diode. So for large load inductance, the load current does not reach zero and we obtain continuous load current. Actually, in the previous lecture, we discussed an RL load. So in RL load, the inductor supply the stored energy from load to source, and when it supplies the energy from load to source, so the current should be zero at pi, but it was not. Uh, the value of current was not zero at pi. It is extending some angle. That angle was theta. That is called your extension angle. But if you talk about that continuous load current means that the value of current must not be zero at any cost. Okay. So in continuous load current, the current, if you want continuous load current, so you have to connect one freewheeling diode in the circuit. So what you can see that to this waveform at point alpha, you are taking the SCR. Current will start to increase. It must be zero at pi, but it is not getting zero at pi. It is extended 3 to 5. And after 2 pi plus alpha, this is again increasing, now this is decreasing, then pi to 2 pi freewheeling diode is conducting. So current is not getting zero. So by using freewheeling diode, you can continuous the load current, and we can continue the load current. So you can see that single phase half wave control rectifier with our general load. So this is your generator load R, L, and E. This is your half wave rectifier. You are using only one SCR. This is your supply minus plus, and this is your resistance, inductor, and E. So this is your output voltage, right? Now gamma. If you talk about the extension angle gamma, that is sine inverse E upon Dm. For trigger angle alpha is less than gamma. So the thyristor conducts from omega t is equal to gamma to theta. For trigger angle alpha is greater than gamma, and a thyristor conducts from omega t is equal to alpha to beta. So this is a 0 to alpha Bn pi load voltage. This is 2 pi and 2 pi plus alpha. So we can start from this point that the output voltage is V naught. So it is starting from 0, and you can see that when thyristor is triggered at point alpha, so voltage start increase. At this point, the voltage should be zero, but it is extending some angle pi, that is beyond pi. So this is your beta, and for negative half cycle it will not conduct. So this is conducting from alpha to beta. It is beyond the angle of pi. So you can see that input voltage Vs is equal to Vm sin that is your input supply voltage. V naught is equal to Vm sin omega t, that is your output voltage. For omega t is equal to alpha to beta, V naught is equal to E. For omega t is equal to 0 to alpha, and for omega t is equal to beta to 2 pi. So when the thyristor is triggered at a delay angle of alpha is greater than gamma, the equation for the circuit can be written as Vm sin omega t is equal to IR plus, and this equation can be written from this circuit. So V as is equal to IR plus LdI by dt, and this is E. So you can apply KVL in this circuit and you will get this equation. Vm sin omega t is equal to I naught into R plus LdI naught upon dt plus E. So alpha is less than omega t is less than beta. So the general expression for the output load current can be written as I naught is equal to Vm upon Z sin omega t minus phi minus E upon R plus A e to the power minus t upon 2. So you can easily get the output voltage waveform and output voltage and the output current by these equations. Now, the formula for impedance is equal to Z is equal to R square plus square of L omega. This is your load impedance. Phi is equal to tan inverse omega L upon R. That is your load impedance angle. And tau is equal to L by R. That is your load circuit time constant. So the general expression for the output current can be written as I naught is equal to Vm upon Z sin omega t minus phi minus E by R plus A e to the power minus R by R into t. So to find the values of the constant, apply the initial condition at omega t is equal to alpha, load current I naught is equal to 0, equating the general expression for the load current to 0. At omega t is equal to alpha, we get I naught is equal to 0, V z sin alpha minus phi minus E by R plus A e to the power minus R by L into alpha upon omega. So we obtain the value of constant A as A is equal to E by R minus Vm upon Z sin alpha minus phi e to the power R upon L omega into alpha. Substituting the value of the constant A in the expression for the load current, we get the complete expression for the load current. So not is equal to Vm upon Z sin omega t minus phi minus E by R plus E by R minus Vm upon Z e to the power minus R upon N omega t minus alpha. So you can derive an expression for the average or DC load voltage also. So by these equations, you can easily derive the DC voltage. So V naught DC is equal to 1 upon 2 pi integration from 0 to 2 pi. V naught into T omega T, and V naught is equal to 1 by 2 pi integration 0 to alpha V naught into T omega T, and alpha to beta V naught dot d omega t plus beta to 2 pi v naught d omega t. When you solve this equation, you will get the output DC voltage. So V naught is equal to Vm sin t. That is output load voltage for omega t is equal to alpha to beta. V naught is equal to E for omega t is equal to 0 to alpha, and for omega t is equal to beta to 2 pi. So output DC voltage is equal to 1 by 2 pi integration 0 to alpha E dot d omega t plus Vm sin omega t beta to 2 pi E. So this is all about your output voltage equation for RLE load. And by solving this equation, you can easily get the expression for output voltage, DC output voltage. This is the RLE output voltage, conduction angle, which is given by delta, which is equal to beta minus alpha. And the RMS output voltage can be calculated by using the expression V naught RMS is equal to load 1 upon 2 pi integration 0 to 2 pi V naught square into d omega. So this is the equations by expression by which you can easily calculate the output DC voltage for half wave controlled converter with RLE load. So basically what we are doing of chopper and voltage commutated chopper or classical chopper. So this is the diagram by which the voltage commutation process is operated. So you can see that there is an inductor which has the value of Ls. This is called your source inductance, and this is your commutation circuit actually. So T1 you are using one thyristor T1, capacitor C and thyristor T2 and D1 and L, and another one is your freewheeling diode. So this is your commutation circuit, voltage commutation circuit. Now let's start with your capacitor. So to start the circuit, capacitor C is initially charged. We are taking that this capacitor is over here, which is already charged, and one plate is positive by triggering the thyristor T2. So if is this is your this thyristor is turned on, we are turning on this thyristor. So you will see that the A terminal will be positive and B plate will be negative of the capacitor. Now, capacitor C gets charged through VSC and T2 and load. So when you turn on this SCR, then the capacitor will start to charge through this loop. You can see Vs, Ls, capacitor C, T2 and your load. Okay. Now you can see as the charging current decays to 0, thyristor T2 will be turned off. When this is going to be 0, then the thyristor will be turned off, and with capacitor charged with plate A positive, the circuit is ready for operation. So we assume that the load current remains constant during the commutation process. Now, for convenience, the chopper operation is divided into 5 modes: mode 1, mode 2, mode 3, mode 4, and mode 5. So in mode 1 operation, uh, you can see this is your diagram. So let's uh, let's start with your mode 1 operation. You can see that in this mode, the capacitor is charging through your thyristor T1, because thyristor T1 is in your forward biasing, because this terminal is your positive and this is your negative terminal. So thyristor will start to charge, and thyristor will start to conduct, and the current is flowing through this uh, direction. This is your load current, and the capacitor current is flowing through this path: capacitor, thyristor T1, D1 and L. Okay. In mode 2, when your capacitor start to discharge, or you can when it gets turned off, sorry yes, when it gets turned off and you turn on this SCR, this terminal will be positive and this terminal will be negative. Because of this terminal, the thyristor T1 will be in turn off mode, and the thyristor T2 will start conduct. So the load current will flow through this path, through this input inductor, capacitor voltage, thyristor T2 and IL. Now let's come to your third mode, which is in which your freewheeling diode will come into the conduction mode. So after this mode, when capacitor start to discharge, then this terminal will be positive, this will be negative. So the current will start to flow through this freewheeling diode. Okay, so current will start to flow through this freewheeling diode, and mode 4 operation, you can see that this diode will come into the picture again, and the load current will flow from source to load. And in the fifth operation, only freewheeling diode will conduct, because this part will be turned off. So only this portion will be conduct, and the current will flow through your freewheeling diode. So let's discuss in detail that what is your mode 1 operation. So in mode 1 operation, thyristor T1 is fired at T is equal to 0. You can see over here that the supply voltage comes across the load, and the load current IL flows through T1 and load. At the same time, capacitor discharges through at the same time, because you can see that the voltage is across the capacitor is your VC. When the current starts to flow, then the capacitor start to discharge through this path. Okay, so capacitor start to discharge through T1, D1, L1 and C, and the capacitor reverses its voltage. So this reverse voltage on capacitor is held constant by your diode D1. Okay, it is held by your diode D1. So capacitor discharging current ICT is equal to V under root C by L sine omega t, and where omega is equal to 1 upon under root LC, and capacitor voltage is equal to V cos omega t. Now let's come to the mode 2 operation, because in first operation capacitor start to discharge, so the this plate will be positive and this plate will be negative, and you can see it is the favorable condition for thyristor T2, so you can turn on this thyristor at this point. So thyristor T2 is now fired to commutate thyristor T1, and when T2 is on, capacitor voltage reverse biasing and T1 and turns it off. So the capacitor discharges through the load from minus V to 0. So discharge time is known as your turn off time. So circuit turn off time is given by TC is equal to VC into C upon IL, which is very important because sometimes some numerical is asked, which is based on your turn off time, and which is denoted by your is your load current, and turn off time of circuit depends upon the load current, because if this load current is high, the time will be less. If load current is your low, then time will be high. So DC depends on load current, and it must be designed for the worst case condition, which occurs at the maximum value of load current and minimum value of capacitor voltage. Now, capacitor recharges back to the supply voltage with plate A positive. This time is called the recharging time, and it is given. So the capacitor recharges back to the supply voltage, and with the plate A is positive. So this time is called the recharging time, and it is given by TD is equal to Vs into C upon IL. So the total time required for the capacitor to discharge and recharge is called the commutation time. That is denoted by TR is equal to TC, the charging time of capacitor, and this is your discharging time of capacitor. Because in first mode the capacitor was charging and in the second mode the capacitor was discharging. So total turn of time of the SCR is TR is equal to TC plus TD. Now let's come to the next mode, that is at the end of mode 2 capacitor has recharged to Vs and the freewheeling diode starts conducting, because in mode second and the diode was charging from your supply voltage. So in that case this will be positive and this will be negative, so diode will be turned on, and the thyristor so the freewheeling diode will be turned on, so starts conducting and the load current decays. The energy stored in the source inductance Ls is transferred to the capacitor. So hence capacitor charges to a voltage higher than your supply voltage. So T2 naturally turns off. So you can see that the terminal voltage of this the terminal voltage of this thyristor will be less than to this voltage. So the voltage difference between these two terminal will be negative, and this thyristor becomes in your reverse biasing, so it gets turned off naturally. So the energy stored in source inductance Ls is transferred to the capacitor. So hence capacitor charges to a voltage higher than supply voltage. So VT2 naturally turns off. So in this case, the equation for this capacitor voltage can be written by this VCT is equal to Vs plus IL, because you can see the voltage across the capacitor will be equal to your Vs plus the inductor voltage. So this voltage will be high than your supply voltage. Okay. So this terminal voltage is high your than supply voltage. So thyristor will be turned off. And from this diagram, you can see VCT is equal to Vs plus IL root Ls upon C sine omega St, where omega S is equal to 1 upon under root Ls C. Now let's come to the next mode of operation, which is your mode 4. In this operation, you can see that the diode D1 also comes into the picture with inductor L. So the load current is also flowing in this mode. Now, capacitor has been overcharged. Its voltage is above supply voltage. As I previously said, that in your mode third, the capacitor voltage was the sum of this inductor voltage and this source voltage. So in mode 4 operation, your capacitor is charged, which voltage is above your supply voltage. So capacitor start discharging in your reverse direction. So you can see that in mode 4 the capacitor becomes start in discharging in reverse direction, so it becomes your negative, and capacitor start discharging in reverse direction, hence capacitor's current becomes negative. So the capacitor discharges through Ls, Vs, freewheeling diode D1 and L. When this current reduces to 0 D1, okay, you can see yes, it is discharging in this mode. When this current reduces to 0, then diode D1 will be turned off. Okay. So when this current reduces to 0, D1 will stop conducting and the capacitor voltage will be same as the supply voltage. When this will discharge totally, it will start to, you know, it will, there will be no current through this diode. It will be turned off, and this voltage is equal to your this voltage, right? And the capacitor will be charged equal to your supply voltage. So it will stop conducting and the capacitor voltage will be same as the supply voltage. Next, come to the mode 5 operation. When the diode turned off, there is the only path which is remaining, that is your freewheeling diode. So the load current will start to flow through this freewheeling diode. So both thyristors are off and the load current flows through the freewheeling diode. This mode will end once thyristor T1 is your fired. So you can see from the diagram that this is your capacitor current, okay, and which is equal to your inductor current at this time, and this is your current which is flowing through the thyristor T1. So this is your waveforms of charging and discharging of your capacitor. Now these are the voltage waveforms across your capacitor, and uh, this is the voltage which is equal to your thyristor T1. This is your output voltage, okay, and this is your voltage across your capacitor. So when your thyristor capacitor voltage is negatively charged, then at that case the voltage across the thyristor is equal to 0, okay. So by these waveforms, you can easily understand that by the capacitor and by the method of charging and discharging methods, how can we commutate your chopper. Now let's come to the disadvantage of this method, because a starting circuit is required to triggering your SCRs T1 and T2. So this is the main disadvantage, that you need another circuit which is used to turn on or turn on your thyristors. So starting circuit is required, and the starting circuit should be such that it triggers thyristor T2 first. Then load voltage jumps to almost twice the supply voltage when the commutation is initiated, as we have already seen our mode third, in which your your capacitor voltage was double at your input voltage, and the discharging and charging time of commutation capacitor are dependent on the load current, and this limits high frequency operation, especially at low load current. So chopper cannot be tested without connecting load. Resulting in increasing its peak current rating. So thyristor T1 has to carry load current as well as resonant current, resulting in increasing its peak current rating. So what is next is your that was your voltage commutation. Voltage commutation means when the voltage appearing negative across your SCR, then your thyristor was turning off. Now another procedure is your current commutation. So by making your load current negative or reducing your load current, the thyristor can be turned off. So this procedure is called your current commutation. So what is meant by current commutation? So chopper is used to change the DC level of voltage, and it is your DC to DC converter. Now, in current commutation chopper, as the name suggested, chopper is commutated by current pulses. So in this process, a current pulse is made to flow in the reverse direction through the conducting thyristor, and when the net thyristor current becomes 0, it is turned off. So there are some assumptions which you have to take before your current commutation process. So some assumptions are that load current is your constant, SCR and diode are ideal switches. RC is a large resistance such that it can be treated at open circuit during the commutation interval, and the energy for commutation comes from energy stored in capacitor. So capacitor is charged to EDC so that energy for commutation is available. So this is the circuit of your current commutation chopper. So in current commutation chopper, you can see that this is the diagram where you are using diode D1, thyristor T1, auxiliary thyristor which is your TA, and another inductor which is L, and your uh, RC. So the value of RC must be high, that it will behave like a open circuit, and this is your diode D2, this is your capacitor C, and this is your freewheeling diode. So this is the diagram of your current commutated chopper. Now there are 5 mode of operation, which is uh, which is here. So this is your mode 1. This is your mode 1. This is your mode 1. This is your mode 2. This is your mode 3 and mode 4 and mode 5. So in first mode, let's start with your first mode, that let's start with your first mode, that in this case the resistance is very high, so it will behave like a switch and it is behaving like your open switch. When supply voltage is connected through this circuit, then you can see that the capacitor, the voltage across the capacitor is your this plate is positive, this plate is your negative, and you can see that the capacitor start to discharge through this inductor TA and this inductor. When it discharges, the capacitor voltage, the voltage across the capacitor becomes reverse biasing. This plate is negative, this plate is positive. So SCR becomes turned off, TA, auxiliary thyristor, because the you can see in this diagram the thyristor TA will be turned on only when this terminal is positive and this is your negative terminal. Initially it has the voltage across this capacitor is your VC. When we connect it through it supply, then it start to discharge from this circuit, and when capacitor discharges, the voltage across this capacitor, this plate becomes negative and this plate becomes positive. So thyristor TA turned off. Now in mode 2 operation, thyristor TA is turned off, and you can see that thyristor mode in mode 1, the thyristor TA is turned off, and you can see in this diagram that when it is turned off, the this terminal is negative, this terminal is positive, so it start to discharge through this path. Okay, it start to the capacitor current start to flow through this part, and you can see from this diagram, when capacitor current start to flow through this diagram, the diode will remain in your off mode, because the thyristor D1 will remain in your off mode, and the current which is flowing through this thyristor is IT1 is equal to your load current minus your capacitor current. Okay, now let's come to the mode third. In mode third, the thyristor will be turned off, because when it start to discharge, then this terminal will be negative and this terminal will be positive. So when this terminal is negative and this terminal is positive, diode D1 will turn on. It will turn on, and when it will turn on, the diode D1 will start to conduct, and the current across through the diode is equal to IC minus I naught. And in mode 4, that you can see that this D1 T1 TA will be turned off. This diode D1 is turned off, T1 is also turned off, and TA is also turned off, and the load current will start to flow through this circuit, capacitor, inductor, and is your this diode D2. So the current will start to flow through this circuit. In fifth mode, this diode will be uh, only freewheeling diode will be conducted, because this diode will be turned off. So the current will flow only through this freewheeling diode. Okay, so this is your current commutation process, in which it has 5 modes, and these are the waveforms of this voltage and current waveform of current commutated chopper. Now, next is your load commutated chopper. So this is the diagram of your load commutated chopper, where you are using 4 SCR and 1 capacitor and 1 freewheeling diode, which is very simple circuit. And these work in only 3 modes: mode 1, mode 2, and mode 3. From 0 to T1 mode 1, you can see that the thyristor T4 and T3 will remaining off, and T1 and T2 will conduct. So the load current will flow through this path. In this case, this terminal is negative and this terminal is positive, which is making your capacitor in your reverse biasing. So in mode second, the thyristor T1, T2, T3, T4 will remain in off condition. This is your terminal positive, this is your negative, so it will make these T1 and T2 will be turned on. Only freewheeling diode current will flow through this freewheeling diode. And in mode third operation, the thyristor T3, T4 will be turned on again, and T1 and T2 will be turned off. So what are the advantages of current commutated chopper? So the capacitor always remains charged with the correct polarity. Commutation is reliable as load current is less than your peak commutation current ICP, and the auxiliary thyristor T2 is naturally commutated as its current passes through your zero value. Now, next is your multi-phase chopper. So this is your two-phase chopper, in which you are using 2 choppers and 2 inductor and 2 freewheeling diode. So the multi-phase chopper consists of 2 or more choppers connected in parallel. So inductance L is assumed to be sufficiently large such that each chopper operates independent of each other. There are few modes of operation. One is your in-phase operation and another one is your phase-shifted operation. So uh, you can see from the diagram that this is the waveform your in-phase operation, and this is your phase-shifted operation. So in phase operation, all the parallel connected choppers are on and off at the same instant. Input current I is equal to I1 plus I2 is doubled, and the operation is equivalent to a single chopper operation, and the frequency of harmonics in the input current is equal to 1 by T switching frequency of each chopper. And next one is your phase shifted operation. So phase shifted operation, different choppers are on and off at different instants of time. For alpha is equal to 30 degree, chopper 1 is on. For 0.3 T, which is your duty cycle, from T is equal to 0, chopper 2 is made on, such that I1 plus I2 is in periodic in nature. So frequency of I is doubled and its ripple current amplitude is I max minus I minimum is called. So frequency of harmonics in the input current is 2 into 1 by T. Size of filter is reduced as a result, making phase shifted operation of multi-phase choppers are most preferred. So for different duty cycle, you can draw the waveform of this phase shifted operation. Okay. So multi-phase choppers are used when large load current is required. These are the advantages and disadvantages of multi-phase chopper. Advantage is that input current has reduced ripple amplitude and increased ripple frequency. So as a consequence, the size of the filter is reduced. Disadvantage is that the extra commutation circuits is used, additional external inductors are required, and complexity in the control logic. These are the references of this lecture, PS and NPTEL, where you can go and get the lecture. And there are some MCQs which is based on this lecture. So first question is that in the type of chopper, two-stage conversion takes place, which is takes place in your AC link. Chopper's converter is used for DC to DC conversion. A chopper may be thought as a inverter with DC input. A chopper may be thought as a inverter with DC input, DC equivalent of an AC transformer, diode rectifier, or DC equivalent of an induction motor. So chopper is always behave like an AC transformer, because transformer is also convert your input voltage to step up or step down your voltages, AC voltages. Like this chopper is also used to step up or step down your DC voltage. Next is your which device can be used in a chopper circuit. So there are a few switches which can be used in a chopper circuit, which is your BJT, MOSFET, and GTO. So these three switches can be used as a chopper. A chopper is a time ratio controller, AC to DC converter, DC transformer, and high speed semiconductor switch. So chopper is your high speed semiconductor switch. Now sixth option is, what is the duty cycle of a chopper? So duty cycle of a chopper is turn on upon T, means the turn on time of chopper is divided by your total time, uh, or you can write this equation T on upon T off plus T on. The load voltage of a chopper can be controlled by varying the uh, duty cycle, firing angle, reactor position, extension angle. So the load voltage of the chopper can be changed or controlled by varying your duty cycle. Next is your the value of duty cycle alpha lies between maximum value of duty cycle is always less than or equal to 1. Okay, so C is the right answer for that. Next is here, if T is the time period for a chopper circuit and alpha is its duty cycle, then the chopping frequency is alpha upon T on. Now last question, find the output voltage expression for a step down chopper with Vs as the input voltage and alpha as the duty cycle. So the answer is your output voltages depend upon your duty cycle in your step down chopper. So the equation for step down chopper will be V naught is equal to Vs into alpha. So this is all about your commutation circuit and chopper. Yes. Thank you.